Okay, so here's where we were last time. We were talking about this odd little calculation here for no apparent reason, right? And I want to recognize this comes out of nowhere. It seems like a completely arbitrary question to ask. But let me just remind you what the question was. Given a curve, right, we can talk about a neighborhood of that curve, namely all the region that's you might say no more than a certain distance away, or in this case, I'm going to define it by imagine that you have a cross-sectional area that you're kind of dragging along the curve, something like that. And looking at all of the fluid inside of that yellow region, with each little piece of that fluid moving according to our whatever the flow is, right? Whatever the vector field says that fluid is doing, as it flows along. Like so. To some extent, it's going to be flowing along the curve. Right? Each little piece of fluid, to some extent, will be flowing along the curve. We ignore the part that's not along the curve. Okay. And what do I get when I combine all this together? And the way I like to say this is I want to know the total rate of fluid flowing along the curve. Why we are interested in such a thing will reveal itself in a minute. Well, we did this calculation last time, and this is about where we ended last time. This amount of volume is just area times thickness, right? This area of this base right here is our given area A. The thickness, you might call it, is just that whatever the length of that little piece of curve is, so ds. And the extent to which it's flowing along the curve is literally a component, and of course components are computed with a dot product with the unit vector, in this case the unit vector along the curve, namely the unit tangent vector. So putting it all together and adding up over the entire curve, right, adding up for all the little chunks of fluid, we get as total we get that this quantity is this expression right here. And I think this is where we ended last time. So who cares? It's a pretty reasonable complaint to have here. Okay, so let me try to explain what we care about this. First of all, I'm going to talk about this area for just a second, that cross-sectional area. Notice the way that cross-sectional area shows up in our answer is that it's just a factor. And this is really unsurprising if you think about it. More area just means more fluid, right? So really not surprising, right? So I feel like of course it should be proportional to area, and so a better way perhaps to think about this question is not how much actual fluid is moving along the curve, but since area is obviously going to be a factor, let's talk about how much of this fluid flowing along the curve is there per unit area. And that's a way of kind of getting rid of this area factor so it's not messing up our result. And with all that said, we now have a really nice interpretation of vector line integrals. And here's how that works. You look at this equation right here. Right? And we're going to take this as an interpretation of vector line integral, because you can see right here in the equation what that vector line integral is quantity per unit area. Or let me say that a little bit differently. This vector line integral represents how much the fluid is flowing along the curve per unit area. So now I presented this. You may recall last time I kind of apologized in advance for it's going to seem weird to ask why are we interested in this question? And I claimed there would be a punchline, and here it is. The answer to our question is something we were interested in the first place. Right? We were interested. The whole reason we sort of went down this road is because we're trying to come up with some way to make sense out of what a vector line integral means when you're talking about a fluid flow. And what we posed as the question is in fact really the answer to our true question, which is what on earth sense can I make out of vector line integrals in this context? And so here's your answer. A vector line integral, what that represents in the context of fluid flows is how much the fluid is flowing along the curve. Right, in the sense that discussed above. And, per unit cross-sectional area, of course, again, that cross-sectional area is going to be there. So, really nice interpretation. Yeah, question?
So you said it's like how much it's flowing along the curve.
Yeah.
Where does the rate part come in?
What do you mean the rate part?
Like, I'm confused about, I thought that, the expression that we have, if you, looked at it with respect to time, then you would have a rate.
Yeah, so there's a rate right here in the vector field. So keep in mind, when you're talking about fluids, the vector field represents the velocity of the fluid, and that is distance per unit time.
Okay.
Yeah, so that's where the rate comes in. Yeah. Right. Okay. Good. Okay. Anybody else? Okay. So we have ourselves a reasonable interpretation. I want to confess that there is something unsatisfying about this interpretation, because isn't it nice when answers to questions are physical quantities that we already have familiarity with, right? So, for example, if the answer to this question had been something like, mass, then yay, we're happy with that answer because we know what mass is. Or if the answer had been work, cool, because we know what work is. Right? The dissatisfaction, the anticlimactic aspect of this interpretation is just based on the fact that we have no previous familiarity with this. Why would anyone have any interest in how much the fluid is flowing along a curve? And let me just say there are lots of applications of this idea. My favorite one, not that I have a lot of experience with engineering, but if you look at how airplane wings work, right, kind of a big deal, right, very important in practical applications. One very important way that they use to get their hands on how this phenomenon of how an airplane wing works is they recognize that there is a fluid flow, namely air, right? And there is a curve, namely the sort of the perimeter of the airplane wing, the cross section. And it turns out that this interpretation is pretty key in making sense out of how airplane wings work. So, unfamiliar previously, but really important physical idea. Okay, now we're going to talk about a special case of this. This statement is true in general, right? But we tend to focus on the following special case, namely how to make sense out of a vector line integral when our curve is a closed curve. We're going to find that there's a lot of math that is closely and importantly connected to this specific special case, vector line integral around a closed curve. So this particular special case is important enough to have a name. It's called circulation. We very often use this lowercase Greek letter sigma to represent circulation because of the vowel sound that it shares with sigma. And now let's just kind of think that through. How would we, how do we adjust our interpretation of this vector line integral based on the fact that the curve is a closed curve? And here's the idea. If you have a closed curve, then you can draw it like so. It starts and ends at the same point. But now let me talk about the tangent vectors to that curve. The tangent vector, you might say, starts straight up, right? And then it kind of turns around to the left, and then it turns around down, and then it, et cetera, et cetera. That tangent vector literally makes a complete circle, right? It goes around and then right back to where it had been. The direction that a closed curve points, assuming that it's differentiable, doesn't have any corners, nothing weird like that, that direction that the unit tangent vector points will always go in a complete circle. So if the vector line integral is measuring the extent to which the fluid follows the curve. And if the curve is going around in a circle, you could make the interpretation that this expression here is measuring the extent to which the fluid is also kind of going around in a circle. And thus, I think, a pretty reasonable motivation for the term circulation. Okay, so anyway, that's the term. I don't know if y'all had the same experience I did when I was growing up, but my dad was constantly going around the house and opening certain doors and closing certain doors, and he was always explaining why. Well, it's because of the air conditioning, and we need to allow circulation, or we don't want to circulate in certain areas, but we want to circulate in other areas. And I don't know how much y'all know about how air conditioners work, but somewhere in the house. In our house, it was in the attic. There was this thing that got really cold, right? And you take a course in thermodynamics, they'll talk about how that works. But this thing got really cold, and air would blow over the cold thing, right? And then nice cold air would come into the house. But if you think about it, then that air that comes into the house needs to push other air out of the house and back into the attic to take the place of. So the air has to kind of go around in a sort of a loop, right? And if you allow liberal use of the word, it has to go around in a circle, right? And so the process of air following a curve like that, circulation, right? And so I didn't realize it at the time. I'm not sure if my dad realized it either, but he was using a multivariable calculus reference there. So, anyway. Okay, so here's one other well, actually, let's look at these examples here real quick. Let's imagine this closed curve right here, oriented as indicated. And now let's imagine we have a fluid flowing as drawn, right, like this. And now the question we're going to ask is, without computing algebraically, we don't have any algebra to work with here, but if I would just go based off the picture here, to what extent do we see circulation in this picture? And keep in mind, our interpretation of circulation is that it's a measure of the extent to which the fluid is flowing along the curve. And I got to tell you, I see a lot of that in this picture, right? The fluid is flowing exactly along the curve, right along in here. And then as the curve changes its direction, the fluid, likewise, I mean, this is just a nice example, also kind of changes its direction. And so we're picking up a lot of line integral everywhere along this curve. Everywhere along this curve, the fluid is flowing along with the curve. So, as you'll see down here, the circulation, in this case, is large positive. Okay. All right, so now let's consider this next case down here. This closed curve, a very similar looking closed curve. You'll notice, however, going the other direction. And our vector field is exactly the same as it had been, seemingly going kind of, if you will, along the curve, kind of. Right? But something is importantly different. You'll notice that even though the fluid is going parallel to the curve, it's going in kind of the wrong direction. Right? The curve, for example, up here, the curve is going that way, the fluid is going that way. So, I mean, yeah, it is going parallel to the curve, but in a backward sense. So, if you look at these dot products, the direction that the vector field is pointing, the direction that the differential, the position differential is pointing, those are dot products of vectors going opposite directions. And so, we're picking up at every point along this curve negative contributions to this line integral. And since that happens the whole way around it, we should expect this line integral, namely that circulation, to be negative. Does that make sense? Yeah, question.
Which direction would the tangent lines?
Yeah, so the unit tangent, so the t, which of course is built up inside of that dx there, right? The T is, oh gosh, if I can get that. What did I do there? There we go. Color choices. The T that is inside of the dx vector is always tangent to the curve and in the direction of the orientation. So in the direction the curve is going. Yeah. Okay, so these two pictures that you see right here are kind of your basic, standard, easy starter examples of positive circulation versus negative circulation. A little bit weird because you notice the vector field's the same in both cases, right? And why do we get positive for one, negative for the other? Because we're ultimately asking different questions. In this first question, we're kind of asking, to what extent is the vector field circulating counterclockwise? Because the curve is counterclockwise. Whereas in this second example, we're kind of asking, to what extent is this fluid circulating clockwise? Because our curve is oriented clockwise. So we get the same fluid, we get opposite answers because we're asking opposite questions, you might say. Okay, so last observation I'll make is that not all questions are this clear-cut. You'll notice that the closed curve here, like so, our vector field, again, same vector field. In some places, the fluid is flowing opposite of the direction of the curve. In some places, the fluid is flowing with the direction of the curve. So some terms here are going to be positive, some are going to be negative, and at a quick glance, it's not immediately clear whether this is going to be positive circulation or negative circulation. So the circulation here, who knows? And sometime soon we'll be able to take a slightly different point of view on how to answer a question like this. But for the moment, we just have to kind of throw up our hands. Okay. So last thing I want to say about circulation, just another interpretation. I pose the scenario of imagine that you're taking a leisurely hike in the woods and you come across a little stream, right? And at the time of year when, let's say, when leaves are falling, right? And maybe there's some leaves that have fallen into the stream. And what do leaves do when they fall into the stream? They float downstream. Okay, but leaves don't just move. Leaves, imagine my hand being a leaf, right? The leaf, as it's flowing downstream, might also be kind of turning as it goes. You've probably seen this kind of thing, right? So what determines how it's going to turn? And I would make the case that circulation is a pretty good model for trying to figure that out. So if I have a leaf like so, let's just imagine. And if I want to keep track of all the different ways in which the fluid, as it does whatever the fluid is doing, right, all the different ways in which the fluid is pushing on that leaf, if the circulation is consistently what you might call counterclockwise, well, it's probably morally equivalent. The same thing's happening on the inside, sort of underneath the leaf, because, small leaf, you would expect there to be a consistency. And so when you have in this, per this curve, a counterclockwise circulation, I would expect that leaf would be turning counterclockwise. Right? So circulation is a nice way to kind of get your hands on, at least on the small scale, if we're talking about small things, circulation is an indication of which direction small objects are rotating in the fluid. Does that make sense? Or seem plausible? Okay. All right. Okay. Right. Okay. So there's a couple little examples and small spin-off topics that we need to talk about. The first example, which is really just an excuse to talk about a spin-off topic, always keep your eyes open for good luck. sometimes there is some very good news that happens with geometry that can turn a brutally difficult question into an easy question. And I think that's what this example is here. So you look at this curve. We got a curve, and I'm going to call this a parameterization because I'm giving you the spherical coordinates as functions of time. And you could plug into your conversion formulas and get the rectangular coordinates as functions of time. And I think it's going to get ugly, right? Because let's think just real quick, right? What is the formula for x? X is rho sine phi. Okay, that means I'm going to have sine of t times sine t. I've got trig inside a trig. And then, furthermore, times cosine of theta. So I'd have cosine of a product, including an exponential. It's a nightmare of ugly. So likewise for the rest of the parameterization. So this is a horrifying curve. Okay, now we could, I suppose, take a deep breath and plug in the parameterization and just plug and chug to compute this vector line integral. And I don't know how feasible that works out to be, but I kind of don't want to find out, right? That looks really, really hard. Okay, so here's how we get lucky. There's two really nice bits of good fortune that are apparent in this question. The first is right here. Rho equals 1. Now, phi and theta are doing all kinds of crazy things, but rho, always 1, and that means that we are on the unit sphere. And when you're on the unit sphere, that tells you, and by the way, when I say on the unit sphere, I don't mean momentarily. I mean we are stuck for all of time on the unit sphere, right? Then your dx vector is going to be parallel to the sphere, right? If you're moving on a surface, your tangent vectors are parallel to the surface. Does everybody buy that geometry? Just making a argument by geometric intuition. Okay, next thing. Let's think about our vector field here. Here's our formula for our vector field. Notice it is a scalar function and then times the position vector x. Actually, let me do this. Oh, you know what? I made a bad color choice there. Let me do it like this. Here we go. We have a scalar function times the position vector x. And by the way, there's the position vector x. And let's think this through. And again, let's think about the geometry of this. This is a sphere, right? Centered at the origin. Spheres are highly symmetric. Lots of wonderful geometric conveniences about the symmetries of spheres. And in particular, pure geometric appeal here. This position vector is a radius of the sphere and therefore is perpendicular to the sphere. Now this is a peculiarity of spheres, right? Spheres are the only surface that have this property. But nevertheless, that's how spheres work. If you sort of think about it, right? Wherever you are on the surface of the Earth, for example, right, down is always perpendicular to flat. That's just the way the surface works. All right, so that vector is parallel to the sphere, perpendicular to the sphere, and therefore the field, the vector field itself being a scalar multiple of that, also perpendicular to the sphere. So now all together then, look at these two different conclusions we've had. We've made convenient little geometric arguments about both the vector field and the curve. Here's my f, here's my dx. I'm interested in the dot product, f dot dx. I'm interested, therefore, in this dot product right there, f and dx. Oh, these two vectors are perpendicular. If they're perpendicular, their dot product is 0, And that means that this line integral is 0, and all of the ugliness that we could have had plod through, right? Poof, disappears, puff of smoke, answer 0. Walk away. What do you think? Everybody buy it? So you get lucky like this surprisingly often. The world is full of symmetries. For one thing, the world is full of spheres. Right? Lots of spheres, lots of circles, lots of round things. Right? So there's lots of opportunities for things like this to come up. And again, in my, way back when, when I was in college, I scored many times on this kind of thing, where the geometry gives rise to easy little conclusions that let me just bypass massive amounts of brute force computation. So I encourage you to always be on the lookout for this kind of thing, right up there with symmetries. Right? Symmetries are, again, massively convenient. You save tons of time. Well, likewise, geometric good fortune doesn't come up with every integral, obviously. Right? If it comes up often enough, it's well worth keeping an eye out for. Okay. All right. Okay, this next one is a notational thing, really more than anything else. It's a notational point and a cultural point. So here we go. Old news formula for dx. You can write x prime in coordinates. Right, we take derivatives one coordinate at a time. And then I'm going to say yada, yada, yada. Right? Just kind of carry that through. And what you get very quickly is a formula giving you the coordinates of your position differential dx. It has coordinates dx, dy, dz. So, now who cares? What is this bias? Well, if I just write that down, and keeping in mind that our vector field is going to have coordinates also, let's call it PQR. Okay, well, now I've got everything written in coordinates, and I can literally crank out that dot product in coordinates. And that dot product is that. You see it right there in the algebra. P dx, Q dy, R dz. Everybody with me? It's kind of just plugging in. Yeah. So the upshot is what we have is a new notational option, and that is for a vector line integral, we can write it like this. And we've already seen a few different ways that you can write vector line integrals. Here's a new one. This is what I like to call a coordinate line integral, because it takes the vector line integral and writes everything in coordinates. The vector field is written in coordinates. The differential is written in coordinates. Thus the name. Okay. All right. Now let's try to decide if we like this. Right? Do we like this new notation? I'm going to propose that the starting point for that conversation is, heck no, I don't like this notation. This notation, look at it, it's all big and clunky. Right? There's a lot to write down, takes up a lot of space on the page. I'm going to further complain that this notation is what I'm going to call unnatural, as follows. You look back at this notation over here, the vector field F is very natural. It represents, let's say, force, or maybe fluid velocity. It represents something that's natural in the question. dx represents displacement, how much I literally move as I move along the curve. Also very natural. All of this stuff is coordinate dependent. Q by itself, not really a thing. It's a coordinate of a thing, right? Q is a coordinate of something natural, namely force or velocity or whatever F is. But Q by itself, not really meaningful on its own. So, unnatural, clunky, tedious to write down. Why are we talking about this notation? So here's the reason why. As clunky as this appears to be, it turns out this is bonkers powerful. This notation here, this is what integrals of differential forms look like. We call it differential one forms. And differential forms, extremely powerful. Mathematicians struggled for decades, nearly 100 years, to try to figure out how to take all the theorems that we're going to learn about in the rest of this course. Green's theorem, we're going to start in a few minutes. Gauss's divergence theorem, Stokes's curl, various other big theorems, and how to kind of relate them to each other. And nothing really quite ever really sealed the deal on that until differential forms. So when you're doing sophisticated takes on this material, differential forms is the way to go, right? It's extremely powerful. So this notation being basically differential form notation, very cool in that sense. Now, that said, all of that's beyond this course. We're not going to do anything with differential forms in this course. Not that we couldn't, but I just feel like this course is packed enough as it is. It's pretty abstract and hard to relate to, and I just don't think it fits well with what we're doing. So that's the thing. Even though there are powerful things you can do with this notation, we're not going to do any of those things. Right? And yet, because of all these cool things, this notation is in common use. A lot of people like this notation, again, for good reasons. So this notation is in your future. Whether you like it or not, whether I like it or not, it's going to be out there. Right? I personally think that this notation gets used more than it should. I think if you're going to do powerful, cool stuff with differential forms, then by all means. But if you're just computing, you're just computing the amount of work that it takes to blah, 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 then write it the convenient, compact way is my thought. Okay, nevertheless, a lot of people, for whatever reason, prefer to write it like this, again, even if they're not using the advantages of it. Okay, so y'all need to be prepared. Y'all need to know what to do if you encounter something that looks like this. My advice is that when you see that, you should think this, and in particular, that these things, P, Q, and R, that's just a fancy way of telling you your vector field. And when you see the dx, dy, dz, that's just a fancy representation for the dx vector. Okay. Is that cool? So, heads up. Okay. Okay, last thing I want to talk about before we move along to the next section is the symmetry theorems. As y'all know, I'm a big fan. Big time saver in a lot of ways. Very powerful computational tool. But it doesn't always work, and it's very delicate. Dangerous in that sense that you can try to use it, but then it didn't work, or one of the conditions didn't quite, and it's just massive crash and burn problem. Okay, so here's the good news. Starting with the good news, if you are looking at a scalar line integral, then everything is exactly what you would hope it would be. We have a symmetry theorem. Namely, if your integrand is odd and if your domain is symmetric, then your integral is equal to 0, just as you would hope. And just as we saw in several other versions of this kind of thing, it remains. You got to have both conditions. One of the two is not enough. You need both the oddness of the integrand and the symmetry of the domain. They're both really important. And secondly, you've got to be using the same line for both of those symmetries. So, y'all heard me say all that stuff a million times. First about single variable integrals, then double integrals, then triple integrals, now scalar line integrals. And there's going to be one more version of this theorem coming up in a week or so. Okay. Here's the bad news. For vector line integrals, no such luck There is no odd symmetry theorem for vector line integrals. Don't try to make an odd symmetry argument for vector line integrals. It doesn't hold water. Now, just to give you some quick idea of why this is, here is a curve that, as I have it drawn here, if you'll work with me on my attempt to draw something plausible, it's got a symmetry over that line right there, right? And we can talk about two little pieces of this curve. I can talk about that little piece right there and that little piece right there, and I can talk about how for every piece like this, there's a corresponding piece on the other side that has the same size. This ds is the same as that ds. Everything's looking good in some sense. Until you recognize that your dx vector isn't just made up out of ds's. Your dx vector also involves the t vector. Right? And if you look at the t vector here, and you look at the t vector there, they're not the same. It's pretty easy to see that even in this highly symmetric curve, right, it's perfectly symmetric over this line, these t vectors point in different directions. So they're not the same. They're also not negatives of each other. They're just different, right? So dead in the water. The t's don't have any nice symmetries, so the dx doesn't have any nice symmetries, so we just don't have any odd symmetry theorem. Does that make sense to everybody? Okay, so real careful about that. All right. Okay, but again, scalar line integrals, all good. Okay, so that finishes 6.1. We're going to move on to 6.2 now. 6.2 is the start of a long discussion of, I'm going to call the big vector calculus theorems, which I know we haven't talked about yet, right? But let me just kind of give you a big picture overview of what's coming up in the next several sections. In some sense, the rest of Chapter 6 and the rest of Chapter 7, we're going to see a bunch of theorems that are extremely powerful, they're extremely unexpected, and they all kind of look suspiciously similar to each other. And this is an eyebrow raiser. It's weird. They apply in different situations, but they look a lot like each other. And so now why would this be? And again, this is just foreshadowing, just big picture kind of stuff. The reason that those theorems that we're going to see are so similar looking is because they are actually the same theorem. They're actually special cases of this big sort of unified theorem that just apply in these different settings. Now, we are not going to be able to talk about that big unified theorem. It's way too sophisticated. It's more of that differential form stuff that I've made a reference to. But here's the good news. You don't need to understand all that differential form stuff to be able to capitalize on the fact that it's there and the fact that these theorems have these similarities, right? And in my experience, both as a student and as a teacher, I have been heavily persuaded that a great way to learn these theorems, a great way to develop intuition and instinct and just a general familiarity and sense for these theorems is to focus on how they're similar to each other, right? And then everything you understand about one theorem, by analogy, you can kind of teach yourself the other theorems. It's a really powerful trick. Right? So I'm going to be presenting these theorems not in the way that's most convenient for any one of them, but in the way that I think is most convenient overall, the one that makes them all fit together, the point of view that allows you to see how they're all doing really kind of morally the same thing. So I think that's a really good way to learn this stuff. So anyway, that's the reason why you're going to notice as I go through the next couple of pages of notes here that it's going to seem like I'm maybe being a little heavy-handed about some aspects of this, and that's so that you can see these shared features of these big theorems that we're going to be talking about. Okay. So, with that in mind, here we go. I want to reinterpret what we mean by a boundary. Now, I think y'all have a pretty good understanding of the idea of a boundary already, just sort of the generic idea of a boundary. If you have some set, let's say something like this, then the boundary, of course, is this curve that kind of goes along the edge. You might say that the boundary is it's the border, right? It's the thing that separates set from not set, as I like to say it, right? Old idea. Is everybody happy with this idea of a boundary? Okay, so we're going to reinterpret now boundary as being an oriented thing. All boundaries that we're going to talk about in chapters 6 and 7 are not just curves, they're going to be oriented specifically. And so, for example, if I have, a region like this, and that's not the whole region, I just wanted to draw part of the region, and here's my boundary curve like this. Well, this curve, there are two different directions that you can go along this curve. I could go that way, right, or I could go this way. So, I need to tell you, what am I going to call the orientation of this curve? Which direction does this curve point? And the answer is going to be that way. And what do I mean by that way? What specifically is the thing that allows me to decide that for this curve it's that way? And here it is. It's a weird little rule. It is an arbitrary rule. Somebody made this up. Arbitrary choice. And it goes like this. As you're walking along the curve, in the correct direction, the region whose boundary you're talking about needs to be on your left. That's the rule. Always go in whatever direction of your two options, whichever direction it is that puts the region on your left. So one way to think about this, you might imagine the region as being like a lake or a little pretty little pond or something, and there's a little walking trail that goes around. Always walk around on the trail in whichever direction has the scenery of the pond to your left. Okay. So in this case, it's the purple direction I have indicated there. Now, if I were to imagine sort of the top part, maybe this is looking at sort of the northern sort of shore of this lake. I don't know why my lake is green, but anyway. There's my boundary curve. Which way do I walk? Right? I could walk this way, or I could walk this way. Which one of these two different directions would put the lake or the pond on my left? And, well, that way. Right, as I walk in this direction, the lake is on my left. Is that cool? Okay. Now, let me recognize this is arbitrary. Arbitrary does not mean that it doesn't matter. Right? Case could be made that it didn't matter 150 years ago when this first started getting, standardized. Right? And it really was kind of a toss-up at some point. But this is a very, very standard convention at this point. So even though it is arbitrary, even though it is made up, it is extremely standard, and so it is very important that we all stick with the established standard. Arbitrary though it is, this is the established standard. Okay. All right. Now, there is a partial truth that gets bandied about a lot. I think the following is overplayed, and that is that if you have a shape, for example, like this, a lot of people will notice that as you walk in the correct direction, notice For example, there, region's on my left. Here, region's on my left. Here, region is on my left. Notice we're always going counterclockwise. Right? And a lot of people will present this as boundaries are always counterclockwise. And that is not always true. True in this case. Sure. But imagine this little lake over here. This second lake over here has some islands in it. And keep in mind, boundary includes multiple chunks in some sense. You might say your boundary, there's kind of the outside part of the boundary. Oh gosh, there's the outside part of the boundary. Oh, I'm terrible at this tracing business. But there's also the inside part of the boundary, like so. And like so. And as you're walking along the outside part of the shore, then yes, counterclockwise, puts the lake on my left. But notice that if I'm walking along the shore of one of these islands, clockwise is what puts the water to my left. Does everybody see that? Right, so it is. I'm going to say I'm going to have to kind of cross that out. It's just not always true to say that boundaries are counterclockwise. Sometimes it's clockwise. It just depends on which part of the boundary you're talking about. So, as in simple scenarios, right? If you eliminate possibilities like that, if you consider only what we call simply connected two-dimensional regions that don't have any holes in them, right, then yeah, boundaries are always counterclockwise. But it's not a true and general statement. Okay, pausing for questions. How are we doing on this? Everybody buy it? Okay, next. Accumulation. Y'all have heard me talk about accumulation a lot over the couple of months that we've been in this class. And I'm a big believer in this as a concept. For example, mass accumulates over regions. And what we mean by mass accumulating over an area is that if you look at the mass in the entire region, certain amount of mass, whatever that is, I don't know. And then if you look separately at the mass on D1 and separately at the mass on D2, well, the green mass plus the blue mass will give you the whole mass, right? Said differently, you can't make mass appear or disappear just by separating the region into two distinct sections. Right? So here's another one. Population. Right? Population is an accumulating quantity in the sense that it accumulates over areas. In the sense that, if you look at the population of North Carolina as a whole, right, and then if you look at the population of just the western half of North Carolina and just the eastern half of North Carolina, yeah, same, right? You're not going to generate people by drawing imaginary lines, right? All right, so there's this idea of an accumulating quantity. And here's a related example, but this one goes the other way. Here is something that doesn't accumulate. Perimeter does not accumulate over areas. And I think it's really important to recognize that, as much as accumulation is a really nice idea, it's a really important thing to be aware of because we're going to make a lot of use of it. And every time you use an integral, you are using accumulation because the whole is the sum of the parts, right? It doesn't always work. And so in particular, if I look at the perimeter of the whole region, and then if I look at the perimeter of the left half, and if I look at the perimeter of the right half, right, is the green length plus the blue length equal to the red length? Well, no, definitely not. We literally created new perimeter when we divided this into D1 and D2. So this idea of accumulation is not something to take for granted, right? Some quantities, mass, population, other things, some quantities do accumulate, and it's awesome that they do. Because by contrast, other quantities do not accumulate. And the ideas that you use for accumulation, you cannot apply to things that don't have that property. All right, let's see how we're doing on time here. Oh, and I'm out of time. Okay, so we will draw the line right here, and we'll pick up here on Friday. Y'all have a good one.